Hmm?
I was just listening to that sound, so would it be another video?
Yeah, but it's a class actually. Yeah, it's crazy stuff. Yeah. Good evening, everybody. Just to mention that we'll just give it a little more time, just maybe a few more minutes, and see if we'll have more people join, and then we can start. So maybe a minute.
All right, sir.
Thank you very much. Can I ask, we just briefly switched off, I organize them, is it, it's okay? Thank you. Thanks. I'm just introducing the people and then we can think. All right. Good. Here's hoping people can hear me here. Just confirming if you can hear me. Hello, testing. Oh, thank you very much.
Yes, you.
Thank you so much. Yeah. So, really want to take this opportunity to thank everybody who took the time off to come and attend the second seminar in our series tagged as CSC 5741. Actually, it's 2023/2024 CSC 5741 seminar series. So it turns out that these seminars are a part of a postgraduate course called Data Mining and Warehousing offered in the Department of Computer Science. And what we do, I mean, this accounts for the seminars account towards the total course credit for the students enrolled in the course. But what we do as part of the seminar series is we invited speakers from industry and academia to come and give talks that are aligned with what we do in the course. So anything to do with data mining, and specifically data mining techniques that emphasize the use of artificial intelligence and machine learning. And so without further ado, I'm just going to introduce our two speakers. And today's talk is a bit unconventional, although we have done this in the past. I remember before the pandemic, I believe it was 2019, maybe 2020, we invited colleagues from CIDAS and they did a similar thing. So talked about two separate things but interconnected things. It turns out that the talk that is going to be given by Malaizyo Muzumala and Andrew Shawa is part of a much larger project, project that's called the Enterprise Medical Imaging in Zambia project. I do encourage you to find time and poke around the project website. I'm just going to share a link in the info messages. So what we have done is we've partnered with the University Teaching Hospitals. And we partnered with University Teaching Hospitals some 2 years ago, end of 2021 actually, to be specific. So our interest really is to try and figure out what we can do to make radiological workflows efficient and effective, in essence. That's our goal. But what you begin to realize is to attain that goal, we've been doing a series of things. Like, for instance, we're looking at policy issues, right? We've been, designing and implementing some tools which are about to be deployed in the Department of Radiology, so adult hospital at the University Teaching Hospitals. But also, in regards to what's going to be talked about today, and this is our major interest really, we are interested in trying to explore how artificial intelligence can be leveraged, right, to make these radiological workflows more efficient and effective. Also, just to mention that our other cooperating partner is the University of Cape Town, so we're working with colleagues from the University of Cape Town who are working on one of the work packages for the project. In addition, this project has received generous funding from the University of Zambia, from an entity called Data Science Africa, and also Google Research. It's actually the reason why we've been able to do what we've been able to do, because of the money that they've graciously given us. So without further ado, what I'm going to do is I'm going to introduce the two speakers, and I believe their decision was to do the talk in such a way that it's going to be coherent if Malaizyo does the talk first, and then Andrew will give his part of the talk, because they're connected somehow, and then I think they'll invite questions. So just briefly introduce the two. The first speaker is Malaizyo, and his part of the talk is titled Semi-Automated Classification and Detection of Community-Acquired Pneumonia. Now, Malaizyo is a Master of Science by research student in the Computer Science Department. We've been working with him since towards the end of last year, I think it was. But he's also an innovator, a researcher, and he's a starting academic, he calls himself. He's also a co-founder of Lendbox.io, and also holds a bachelor's degree in computer science from the University of Zambia. Okay, he has a deep interest in solutions and problem solving. I was going to say Malaizyo is really one of the smartest, perhaps one of the smartest students I've worked with. But the thing is, most students I work with, I've been fortunate like that. A number of students that I work with, I think by nature of UNZA being what it is, smart students really. But the next speaker is going to be Andrew Shawa. And Andrew holds a degree in Information and Communication Technology Education from the University of Zambia, and a postgraduate diploma in computer science, also from the University of Zambia. I want to also mention here that I've been working with Andrew since he was in third year, I believe. We're working on a number of projects, and in the process, I think we've continued of nurtured that relationship. He's currently involved in the Enterprise Medical Imaging project. He actually works full-time for the project. The project office is at the University Teaching Hospitals, where he utilizes his expertise to contribute to the advancement of healthcare technology. So what I'm going to do is I'm going to unshare my screen, and I'll invite the first speaker to give his talk, and then I'm sure once he's done, we'll transition to Andrew, and then we'll invite questions. Thank you very much. Over to you, Malaizyo.
Okay, forgive the voice, I've got a bit of a cold, but firstly I'd like to thank everyone for taking the time to attend this. It was a very interesting process, and hopefully the lessons learned and what we can transfer here will be exciting for everyone. So I'll get right into it. Yes, so the title of what I'm going to present is the classification and detection of community-acquired pneumonia by me and Dr. Piri. And so an outline of what I'm going to give is what's here. Basically, we're just going to go over an introduction to MIZ. In fact, we might just skim through that very quickly because Dr. Piri gave an introduction at the beginning there. But yeah, we're going to talk a bit about AI in radiology in Zambia. We're going to talk about how we sourced the data to create the models, how we implemented the models, the results in terms of how good the models were, and how the perceptions of these models and the tools which use them were by the experts. And we'll give a conclusion and then a very quick demo of the evaluation interface we used. And so for the introduction of the MIZ project, I'm just going to very quickly say that Zambia has a challenge, and so does the whole world. Zambia in particular has a challenge around medical image interpretation. We have a severe shortage of experts in that field. At last check, it should be 11 experts in public service serving the entire country, which is a ratio of more than 1 million people in the population for each radiologist, which is a serious challenge. And also the nation has continued to purchase more and more imaging equipment, and there has been, because of the success of the involvement of imaging, a huge increase in the need for imaging and diagnosis of patients. So this has made a huge burden. And among the other things Dr. P mentioned, like policies and procedures, image analysis, software tools, one of the things we believe is a potential solution for this is introducing AI into these workflows in different aspects, but I will particularly talk about the semi-automated interpretation, assisting in the interpreting of these images. And so, yeah, artificial intelligence has been a thing in radiology because radiology is one of those fields which is particularly data-driven. It's one of those fields where large amounts of data, which is by its nature, because they report, is a bit easier to label. And so because of that, it's one of those fields which has huge potential for implementation of AI. Another thing which pushes AI in that direction is the fact that it has, as I stated earlier, a severe shortage of experts. So it's one of those fields that's ripe for solutions and which will be implemented and help many people. And so, yeah, in Zambia, as I said, there are 11, or at last check, were 11 radiologists in public service with a severe shortage of these individuals. Now, one of the things, again, which we should consider about AI, which makes it also particularly useful for radiology, is the fact that radiologists have to go through a series of years of learning and interpreting images before they become qualified. They do this as their residents, same as other professions in medicine. But one of the things that's unique about radiology is the more images you've seen, the better off you are. And it's the same thing with training models. So when you're training a model, you want to find a large data set and have it look through the data set and make what we call inferences, like an educated guess as to whether this image has what we're looking for or not, or is part of a certain group of images or not. And it's a very similar thing the radiologists are doing. But one of the things that's an opportunity we have here is, let's say if you have a supercomputer and you have a normal radiologist. If you have a radiologist and they have 40 years to look at images, there's only so many images they can look at between eating and carrying out the rest of the things they do in their life. Whereas if you have sufficient computing power, an AI could look at all the images that are labeled and exist anywhere. It's legitimately possible, which means that if the data is available, you could have an AI which is particularly well trained in a particular field, which is better than any human interpreter ever and will ever be, right? A challenge though here with AI is that unlike humans, where if you have a radiologist, you could teach them on 500 images and they'll get the idea. For AI, it's a lot more challenging, and also that AI is quite narrow in what it learns. You can't teach it as broadly at once as you can a human. So that's one of the challenges there. Yeah. Anyway, another opportunity we have here in Zambia is that while we are behind in these technologies, now the technologies in the world are quite advanced, and we in Zambia have a chance to leapfrog certain stages the developed countries had to go through in the middle between where they were long ago and where they are now. We can adopt certain technologies straight from them and start to implement these in the workflows we have, and that's some of the work which my colleague here will talk about. Yeah. So some of the potential applications and benefits here, and number one, which is direct to the experts, is first and foremost, this is something which the head of radiology at UTH mentioned. She said there's a situation where a radiologist is looking at an image and they identify a problem, but what that causes is in a human, it tends to create a bias against other problems which might also exist in the image. And that's something which you could very well adjust for in AI. It's a very good opportunity in that regard. And also these images which come out of the what we call modalities, which is the X-ray or the CT scan or whatnot, they are very high definition. And what that allows is when it's a human interpreting an image, the image has to get, the irregularity has to get large enough for that human to view it in an image. Whereas for AI, the analysis is carried out pixel by pixel, which means there's a much smaller area it has to cover for it to be identified, and that's a huge opportunity there. Another opportunity there is the classification of images and studies, whether they are into certain, you could have a model which classifies as to whether this is likely in this area in terms of whether it's an issue with pneumonias, or categorizing in terms of diseases to be sent to particular experts and things like that. Another huge area is assistance in the research and report generation. So what happens when an image is requested of a radiologist is it has to be interpreted, and the report has to be written and given to the referring physician. Now, that is another area where AI could come in. These reports are likely very similar in structure, and with the advent of large language models, these could be used to assist in that process, making it a lot quicker and allowing the radiologist to interpret many more reports. And also, just like other professions, the radiologists tend to have to do a bit of research as they are interpreting images. Now, they have platforms for this, which are like encyclopedias for radiology, but it's possible to have assistance from large language models, specially trained on the knowledge in these platforms, which is something which would also assist them in their research and make them fast. And these solutions, like what we tested, could be integrated with their workflow tools. Also, emergency evaluations. Surgeons and other practitioners have to have the capacity to interpret images very quickly. And one of the really good applications of this would potentially be to have these models be able to give a quick interpretation right on the fly, to give guidance to these experts on things which might be above their expertise, which would normally require a radiologist. And then we could get follow-up from the radiologist, but where it's needed immediately, we could use those there. Also, to free up resources, there are a number of things. The HOD, as I said, also mentioned that things like medicals, for example, where a person takes a chest X-ray and they need to know, the potential employer or football team or whatever needs to know whether this chest X-ray is normal or not. That's an application which could use AI instead of needing an expert and could free up resources. Another thing she mentioned was age verification, which is a really good use case as well, where they look at the bones and see how old someone is. If there's sufficient data, we could train AI to do that. So yeah, for the training of the models, we sourced our data from various places. We initially were looking for only data sets which have images of community-acquired pneumonia, but we later expanded that to cover other pneumonias. And yeah, that proved very useful. Two of the data sets from our dataset hunt are the ones we used to implement the two models. So I'll start with what we did, what was common to both models. So both models implemented transfer learning. So this is where we start with a base model, which is already trained, and we either add layers to it or change some of the layers in these models. In both these cases, these are convolutional neural networks, so they are in layers. Right? And so you can tweak certain layers or add layers to it. For the classification model, we just added layers, whereas for the detection model, we we changed some. And so the base model for the classification model was VGG16. I believe there's VGG19 now, but this is a large model trained on a large number of images. It's by TensorFlow. You can look it up. It's freely available. Yeah, it's a very capable model. And so we got this, and then we just added some more. This was for the classifier. And then for the detection model, we used a modified version of MRCNN. So there's a gentleman on GitHub called Matterports, and yeah, so we used his version of MRCNN, which is also another model for detection of items in images like people and things like that. But then we twisted it to use that. Yeah. So the interface which we used to evaluate the perceived usefulness of these models had three parts. It had the classification only part, the detection only part, and the combined interface. The technologies used to create these interfaces and the services, I used Flask for the services to interface with the models and make them usable, and I used Next.js 13 for the interfaces. Let me just go back a second there. Yeah, okay. Yeah, that's what we used there in terms of technologies. Yeah, these models were both trained in Cargo. For the classification model, we didn't need to use any accelerator because this was the one I implemented first, and yeah, at the time I implemented it faster. Many lessons were learned, but yeah, we used. We didn't use any accelerator because it took, I believe, less than 2 hours. However, we used an H100 for the detection model. It's an option there. They give you a maximum of 30 hours a week. It took about, I think, 9 hours. It was also, we made the imagery sizing larger than for the classification model, but yeah, it took quite a while. But yeah, many lessons I learned again. Hopefully, maybe there are people here who we can learn further from and can get one of those for the work we're doing of their expensive GPUs. Yeah. Okay, so I'll move on. So here we have results from our interactions with the experts on how they've found the models and based on the interface. So this particular one is what's called the NASA-TLX questionnaire, TLX questionnaire, which is the task load index. So it's a proven tool which assesses how demanding people perceive the task to be. And as you can see, the AI-supported workloads had lower perceived difficulty than the non-AI perceived workloads, apart from the frustration index. Yes, it seems that perhaps there was a bit of a challenge for people in feeling under pressure for the AI aspect, but yeah, in general, people found it a lot less demanding of the task. And so here we have the results from the Term 2 questionnaire. In this questionnaire, we are assessing how acceptable, how willing to use these tools people would be to these tools. And so it looks over a number of different categories, whether they intend to use it. That's a series of questions under each category, and then that's where the results are based. Yeah, it looks at job relevance, whether they think it's relevant to their job, the quality of the outputs, the perceived ease of use, the demonstrability of the results, whether they think it's normal, subjective normal, whether they would voluntarily use these tools. Yeah. So in conclusion, we were able to demonstrate that such tools and models, when implemented into workflows for radiologists, will be perceived to be helpful and reduce their workload. Also, as my colleague will show, these models can be integrated with the very tools, also known as DICOM readers, that the experts we built them for use every day. And more and more models like these can be created for different modalities if we have the resources, and we intend on doing that with time. So now I'll show you a quick interaction with how the models worked. And yes, let me go to that. So as I said there, it had three interfaces, but we were advised, we had a a focus group where we advise to use the classifier detector. And so what we're going to do now is we're going to show you where this is the interface for evaluating the tools. So we're going to have the user select there and then select an image that they think is suspicious. This one was assessing only pneumonia, and so it's a chest X-ray. And so we open that, and the image is presented together with the results of the detection model, which highlight where the areas of the image which are considered to be suspicious. So it seems it's both the bottom quadrants of both lungs, and also it has some text which was also we received input from the experts. So the radiograph is considered to be suspicious for pneumonia by a model with 73% confidence. And yes, some other metadata they can see. With that, I will stop sharing and hand over to my colleague here, and I'll be back at question time if there are any. Thank you very much, everyone.
All right, thanks a lot, Malaizyo. I'll ask, Andrew if he's ready for us. And just to mention here that, for people that have not really dove into this space of AI, it might seem like stuff that Malaizyo was doing was trivial, but quite involving. He's not a domain expert. He's had to interact with a number of, experts on the other side of town at UTH. So quite exciting stuff here. And Andrew, I think, is ready for us. Over to you, Mr. Shawa.
All right, thank you. Can everybody else see my screen?
Yes, we can.
All right, so like mentioned, my name is Andrew Shawa, and I'm going to be continuing from where Mr. Muzumala left off. And this part of the presentation is simply going to focus on the implementation of the intelligent DICOM viewers, which involves the plugins that were built for the Authank PAX platform that is currently deployed at the UTH. And I'll explain or go into details more as we proceed. So I'm part of the Enterprise Medical Imaging in Zambia project, as Dr. Piri mentioned. And most of the details I think you can find using the link I was given. So I'll just go straight into the important part of the presentation itself. So coming to the implementation of intelligent DICOM viewers, it is important to note that automated image interpretation is crucial when it comes to the interpretation of images or medical images in a health setup or in a health environment. So if some of you are familiar with the radiological workflow, or what is known as the radiological workflow, which is simply this process where, for example, if you are a patient and you happen to go to the hospital, let's say you have a broken bone and you want an examination taken. So the radiological workflow simply involves the processes from the time you are examined, where an image is taken of you and that broken part of the body, and the processing of that image, as well as that image being taken to either a radiologist for interpretation, where they have to tell or find out what is wrong with that particular part of the body. And then it also includes things like transcribing reports for the same case that they've handled and ordering an entry. So this is a summary of the radiological workflow, and our part is focused on the image interpretation, which is helping these people that do the interpretation of images work faster and more efficiently, and more accurately, sorry. So you will find that there are challenges that are faced by radiologists, especially in Zambia. As the previous speaker mentioned, we have a serious problem of shortage of expertise in this department or in this area. and you find that the few people that are there are very few people that are trained in this area, and that also means that we also have a very few people with a certain level of experience to work on these images. So that becomes challenging if they have to go through this process of interpreting the images manually. You also find that the manual process itself is time consuming because a person has to sit on a desk many hours trying to look at an image and see what's wrong with certain parts of that image. And this can also cause cognitive overload, where you are fatigued or you are tired from time to time due to long hours that you spend looking on images, trying to figure out what could be the problem. So this solution now comes in, which is the implementation of the plugin to enable semi-automated image interpretation. So we did this with Author Paths platform, as I mentioned before, which is the platform that was deployed within UTH. So what was done was this Paths platform comes with embedded viewers within it. These viewers can be used to open and view images for those people that are responsible for the interpretation of these images. So the intelligent DICOM viewer aspect comes in by enabling these existing DICOM viewers with AI capabilities. So it ties to the topic that was previously discussed by Malaizyo here, where there are models that have been built which can help with the interpretation of medical images. So let's say for a case like pneumonia, there are models that have been built where if you feed it an image, it can tell you if the image you've given it is likely to have pneumonia or not. So with such kind of solutions, this particular implementation came in to try and find a way of enabling these existing DICOM viewers to communicate with the said AI models. So that connection actually acts as a bridge between the AI viewer and the AI model for automatic interpretation, and it also enables us to generate annotations as the AI model is processing the images. So if you're using that DICOM viewer, for example, in this case, and that DICOM viewer happens to have this plugin, you have the option of requesting for annotations using that plugin. So in the actual sense, you're interacting with the plugin, which is sending messages to the AI model in the background and getting back a response and giving you those annotations in real time. And already some of us can already see that this would speed up the process that would otherwise be slow without the use of such tools. So there's a sample image here of what an annotated image would look like if you are looking at it from a viewer. And of course, we are going to give a brief demo of how this actually works after the presentation. But you can see here that on an image, for example, after having used the plugin, you would have an option to get some bounding boxes that would point you to specific areas or areas of interest on this image. So the plugin would actually help to tell you to say, if you want to concentrate, you would want to concentrate on such areas because there might be a likelihood of this area having pneumonia or this area having this type of pathology. Let's say in the case that you have other models working. So this is an example image. And then in order for this to be done, there were two modes of integration that were taken into account. So as we mentioned before, we have the AI models that are doing the interpretation, and we have the working DICOM viewers where the radiologists go and interact with these images. So in order for that seamless connection to be created, with the use of the plugin, which was developed for this author viewer, and then this serves as an intermediary between the DICOM viewer and the AI models, right? And then we also have the web service. So this web service was created to facilitate the transfer of data from the DICOM viewer coming from the plugin, and then it gets this data does whatever processing that has to be done to the images, and then feeds the data to the AI models. And then when the AI model is done giving its interpretation, the service carries that data back and feeds it to the plugin that relays the information to the DICOM web viewer. So these technologies work hand in hand to make sure that there is a seamless connection between the viewer and the AI models, where data can be transferred back and forth, and it makes sure that the person that is working on these images has an easier time working on such images, and this would actually increase or improve the turnaround time for the interpretation of medical images. So obviously this would come with benefits, and one of those benefits is that there is an improvement in terms of accuracy and efficiency of the diagnosis. So the introduction of AI, as well as these smart tools that enable these people to carry out their work faster, would make sure that there is less cognitive overload, going back to some of the challenges that we mentioned, and it would make sure that there is less errors made as a result of maybe someone being less experienced in the field, or maybe someone being exhausted from doing so much work. So you would have these tools, which are not even meant to replace the human working on the images itself, but just help improve how they work. So they are there to help, and that's why it is known as the semi-automated interpretation. They give assistance to whoever is doing the interpretation of images. It also helps to make better informed treatment decisions. This is also related to what we've mentioned before, because these people can get access to interpretations in real time. So, which means the diagnosis is going to come back faster, and you would have enough time to plan on the next course of action if the results are coming in at a quick rate. Those are some of the benefits that come with the integration of AI and these smart tools in the radiological interpretation process. So these two, after the implementation, was evaluated, and the evaluation was conducted in a controlled experiment. And some of the participants, or let me say the participants that were used for this evaluation, were the radiologists from the University Teaching Hospital. You also have radiology registrars, so these are radiologists in training. You also have general practitioners. This is other doctors or physicians that might find themselves working on similar cases that have to do with the use of the same tools. And then after the evaluation was done of these people, they were asked to access or fill in a term 2 questionnaire, just to weigh their interaction with the plugin and see their perceived intention to use the tool. Like, if you were given a tool like this, what were the chances that you would be happy to use a tool like this? How would a tool like this improve your work? How would a tool like this help you interpret images better? So yes, that is as far as the evaluation goes. And then coming to the conclusion, it is safe to say that this is a very promising solution, and it has a lot to offer, and it can bring about a great improvement when it comes to the radiological field itself. So the real-time feedback and automation can lead to earlier treatment, as mentioned before, and better patient outcomes. And of course, there is continued development. For example, like the previous speaker mentioned, these AI models can always be improved to actually aim for higher levels of accuracy, and there's still work to be done, but this shows great promise, and there's a lot of benefits that could come from such kind of innovations. I think that is what I had prepared in terms of the presentation. I'll just walk you through a quick demo just to see how everything works. Can everyone still hear me? Just to confirm.
Yes, it's loud and clear, Andrew. Thanks.
All right, thank you. So what we're looking at here is the UTX Sparks platform, as mentioned before. So this Sparks platform was built off of OSANC. So OSANC is the best platform that was used for this, and some further modifications were made. And this is the platform that you're able to see right now. So I'm just going to walk you through how one would actually get to use the tools that we've been talking about. So if you come here, for example, you have an option to search for specific cases or patients and studies that you would want to work on, assuming this person is a radiologist trying to use this platform. So we have a study like this one, and then if we search and navigate to where we have the user, as mentioned before, we said this platform comes with embedded DICOM viewers that can be used to view these radiological images. So we have the awesome web viewer here that is in yellow. If you can see my cursor here. So if we try to open this image, for example, you can see a plain image here, and on the top right corner there we have some details to do with the patient, and obviously the information has been anonymized. But you can also see there on the very last line where it says AI assistant results, which is blank for now. And after requesting for these annotations, we should be able to get feedback or some sort of annotation text there, which is telling us details about this model and the suspected pathology, as well as some bounding boxes. So this tool itself, if you pay close attention to the top left panel that I've opened, there's this button here that says get annotation. So what this button simply does is if we click on it, it's getting this pixel information, the information about the image, and sending that information to the AI model with the use of the web service that we talked about. So this transaction is happening right now, and you are able to get back the feedback from the model, and this is what you end up having, or these are the results that you get from the model. So as we can see, we have bounding boxes on the image, which might be pointing us to areas that might be that might have a chance of having pneumonia. So if I'm a radiologist, I'm able to tell to say, okay, instead of just fidgeting around trying to see where the problem is, I can just focus on these areas and try to see if there is a problem in this specific area that I've been given. Already that improves the time that I'm going to take to just work on these images. And then if we also pay attention to the top right again, we see that we have some text in red. For example, it will tell you the pathology that is suspecting to be highlighted using these bounding boxes. It will also tell you the accuracy of the model itself, the precision, the recall, as well as the accuracy of the detection. So we have two models working in the background, and it will give you results for both of those models, and also include bounding boxes that are going to point you to the areas of interest. So this is briefly how the plugin works, and that would conclude this presentation. So if there are any questions for me or the previous speaker.
Yeah, you see, Andrew, thank you so much for this. I just wanted to mention here, you know, seldom do you get to tell students just how good they really are, but I want to take this opportunity to just mention that the work that, you know, Malaizyo, Andrew, and Eliza have been doing is nothing short of amazing. I think we are fortunate to have recruited really smart and talented students. People may think that what perhaps Andrew and Malaizyo were presenting is trivial stuff. It is not. Andrew was stuck many times, right? It's taken Andrew, for instance, a little over a year, almost a year, I guess, to actually do this. He was doing this as part of his PDIP in computer science program. And just to give you a bit of context as well, so if you use tools like Google Photos, for instance, what you begin to realize is that you may not see this here, but there's things like facial recognition, object recognition embedded within Google Photos. So the idea is there are models that have been implemented that do that, right? You know how Google automatically detects this is your mother or something, this is your father, this is your brother, right? And cluster or tag those photos like that. What Andrew was doing is building an interface that interacts with the models, whereas Malaizyo was focusing on the models. So without further ado, I think what we'll do is we invite questions. I don't know if people have specific questions for us. There's a ton of information available on the website, but just in case you need clarification on the wonderful work that we have been doing for the last 2 years, please, the floor is open. You can just raise up your hand or something, and then we can interact. Yes, Henry, please, go ahead. We'll start with you. I thought I saw a hand up from Henry, I think, but maybe not. Are there any questions? Or is this one of those presentations which went over people's heads? Yes, Mr. Chilasa.
Hello, can you hear me?
Yes, we can, please.
So my question is just on both the presentations. Like, I want to understand. So you mentioned that they tie into each other. So is this like one of those where like someone interprets the images that are there? So I mean, I'm just a bit confused, but so someone interprets the images and then classifies, oh, this is this, like pneumonia, this is cancer and the lungs and all that stuff. Then they push the results and then they train the model to detect all these anomalies inside the body. And then now Andrew's part comes in where like those results that were done. So now you keep on testing and then you get to the point where it's somewhat accurate so that it helps those who understand these things say, okay, this is somewhat accurate, so we can go with this as opposed to just looking around taking hours. So Andrew's part, so is it one of those where like if they read if they read the information and then Andrew's part comes in where now the doctor wants to give the results to the patient, like, oh, this is what's there. So do they work like that, or I don't know if I made sense. I'm just trying to understand. So that's my question.
Okay, let me let me shoot at that one. So Andrew, you can join in if I leave anything out. Perhaps I didn't give enough detail when I went over the data sets and the training. So as we said there are two models which we implemented in this case. One is a simple classifier, binary, to say whether or not this image has pneumonia. Another one is a detector to say if it has pneumonia and we suspect the pneumonia is here. So for the first one, in both cases, you need to find, because of the sort of training we're using, you need to find labeled data sets where experts, radiologists have gone through and said, okay, this is pneumonia, this is not pneumonia. That is for the classifier. For the detector, it goes even a step further. And we were fortunate enough to find a reasonably large data set. You need to find a data set where the radiologists have not only said that this is pneumonia or not, but have also said that it's here. So the Radiological Society of North America, I believe it is, RSNA, we're fortunate to find that they have a very large data set they made publicly available with almost, 30,000 images, 29,700, which are each labeled to say, this image has pneumonia and the pneumonia is here, where they drew quadrants. They drew on the boxes basically, and then that was later changed into coordinates, which are what we use to train the model. Those coordinates, and after iterating through hundreds or many times, and correcting things, the model is then able to also make guesses on images it hasn't seen as to whether, oh, okay, this one we suspect it does have pneumonia here. And then that model is taken, and then used in a service where once an image is received, so in this case it would be the plugin Andrew made sends the image to this endpoint, this service, and then it does the pre-processing of the image and then feeds that pre-processed image into the model to make the same inference or educated guess interpretation as it was doing in the training, except now it's after a lot of training. So we know how good it is at doing that. And so we trust those results and display them to the user for their confirmation or to assist them in making that interpretation. I think I've answered your question. It sounded a bit like you were mixing the training and the use. So yeah, these are separate. The training is where we use those large data sets where actual experts have labeled to say this is where this is and this is this sort of pathology or not. And then that knowledge is basically stored in the model, which is then used later. I don't know if I've answered your question there.
Yeah, no, you have. Thank you. Sorry, I mixed them up, but thank you.
Thank you so much.
Explained it.
And I think I see one of our colleagues, Dr. Sinkala, now Malaizyo and Andrew probably want to look up Dr. Sinkala because he does research in this space as well. Please, Dr. Sinkala, you have a question?
Yes, I have a question and a comment. My first comment is that thank you very much for bringing this presentation to us, and thank you very much to the two presenters. They have done a lot of diligent work. And my first comment or question is related to how the classification models are working. So for example, if it comes to making predictions on medical images, would want the model to have a bias towards, for example, classifying an image as having pneumonia, even if it doesn't have pneumonia, by adjusting the misclassification cost of the model that you're training. So I'd like to find out if you did such tuning, whereby you kind of, let's imagine if it's a linear model, you can kind of shift the decision boundary towards the negative side, so that the model catches more positive images than negative images. In other words, it's biased towards saying that something is positive than negative, because you don't want to send a patient who may have a disease back home because the model didn't pick up that. You would rather have a patient who doesn't have a disease being diagnosed as having a disease, and then the expert looking at that image and then confirming that the model was wrong. So that is my first comment. I don't know, maybe Dr. Piri or one of your students can come in.
Okay, let me take that one. That was directed at me. So in the implementation of the classification model, it was implemented first, and no, I did not do such weight shifting. However, for the detection model, which also has a component of classification itself in the dataset, there was such weighting. So you find that we're able to achieve a recall on that one of 79%, which isn't perfect, but is a start from something we're doing in Scratch. I later found out that there are certain places, though a lot of people are reluctant to share as far as I've seen, but if you start to contact people and get agreements, you could get access to models which have been better trained privately, and perhaps in the future we could be looking at where they exist and are more accurate than others, implementing those. But for the classification model, no. But that is definitely a point for the future. There's a lot of room to improve this very model or look at others. But thank you so much for that input, sir. And I've looked you up. I'll be probably getting in touch. Thank you.
And just to maybe add, so it turns out that the scope of work for what Malaizyo is doing is ongoing work. He only started doing this towards the end of last year, I think I mentioned, and he's doing a master's by research. So part of what he's supposed to be doing is further fine-tuning the models that he's implemented. Of course, also implementing auxiliary models. We're in a process where we're trying to identify additional potential pathologies that we can incorporate into his scope of work for his master's degree. So that's certainly stuff that he's going to take into account. And just to mention that we haven't really gotten to a stage where we can safely say the pneumonia detection and classification model can be deployed and used at UTH. Not yet. But we are hopeful that by the time Malaizyo is finalizing his work, I think we should be able to perhaps deploy some of these models so they can be used by not radiologists. And this is something that's interesting, right? What you'll find is that a number of informal interactions we've had with radiologists are marred by skepticism, but we made it clear that we and everybody else around the world is not advocating to replace important people like medical practitioners and radiologists, but rather you're complementing what they do. So what I'm trying to say is that part of why we're doing this is the motivation at the very beginning, where we have very few radiologists, 11 as of 2021, they say. Now, if you have 11, the question you should be asking yourself is, when you go to Material Level 1 hospital, who does the interpretation? Well, it turns out that your typical general practitioner will do this interpretation. And so what we're saying is we can help those people that are not necessarily experts, right, by building such tools. But thank you so much for that wonderful contribution. It's stuff that we'll certainly take into account.
All right. Thank you very much, Dr. Piri, for that comment. And I usually go around UTH and other hospitals and I tell the people to say, we are not here to replace any expert, but the experts who are not using AI will be replaced by those who are using AI.
I agree. And I joke myself and I tell people that, we were telling them this when we had the workshop recently, I was telling them, I will be replaced, right? I teach. Teachers, are going to be replaced very, very soon. But medical doctors, not so soon. These people that man these booths we call top plazas are going to be replaced very, very soon, right? But not doctors.
Sure.
Yeah. I think there's a question again from Chama, I believe. Over to you, sir.
Yes. Good evening. Thank you very much for the presentation. It was really, really interesting and very informative. My question is in regards to the model. I just noticed that the focus is predominantly on pneumonia. Do we see you expanding to diseases like TB, tuberculosis, and let's say perhaps you integrate pneumonia, tuberculosis, or any such related disease? Do we see the model kind of putting a distinction in that particular regard? Yeah, pretty much. That's my question. I hope I was audible.
Malaizyo, I don't know if Malaizyo.
Thank you so much for that, Mr. Chama. So actually, we do intend on looking into other pathologies, and an approach for that, though none of this is concrete yet, but an observation I've made is a number of institutions that build AI tools, be it Google or OpenAI. What they tend to do is they tend to build a number of models for different things. So I suspect that the more pathologies we attempt to interpret, the more challenging it could be. We could either send an image to all the models, but that's quite computationally intensive. But what they tend to do is they have models specifically trained on certain steps. So maybe we could have a model which is not perfect, but has a threshold where it says, okay, we think this might be TB, sent to the TB model, or this has reasonably high look for both TB and pneumonia, sent to both, and doing such work to minimize that. But definitely, so long the data is available, if not, we do intend on potentially building our own in-house data sets here at UTH with the platforms my colleague was talking about. We're able to to build data sets, and if we're able to store the reports, we can then label those data sets. So for what's not there eventually, if we continue down this path, we could be able to build custom tools for places like this on particular pathologies ranging, including tuberculosis. Another one which was recommended is pneumothorax. Yeah, a number of things could be done. Yeah, so thank you so much for that.
And also, I think what's important, if I can add on to what Mario just mentioned, is you have to realize that some of these things, if you look at the larger enterprise medical imaging in Zambia project, it's an academic project, right? But what we've done is we've tried to identify work packages which are potentially going to result in some tangible product that will later on deploy. Point I'm trying to put across here is that, there's a school of thought which advocates for taking a more radical approach. Instead of, hunting for experts like yourself, Mr. Kasondesa, and people like Malaizyo, for instance, or Andrew, they argue that what perhaps is more effective is you train the radiologists, right? And this is happening. We see this happening. It's certainly not happening in Zambia, but a potentially viable solution is you incorporate, AI and machine learning into the curriculum, because it turns out that these radiology residents actually, they write exams, right? They go for classes. And it takes 5 years to actually train a qualified radiologist, in case you didn't know in Zambia. So what perhaps would be viable is instead of looking for experts, you try an approach where you can teach people how to build these models, or at least how to find models that they can potentially apply in their day-to-day work and be able to evaluate them. So there are plans for us to look at other pathologies. You may be interested in knowing that we did not dream about pneumonia. We had experts offer suggestions. We looked at literature. So if you look at important reports like I believe it's Zambia, household and demographic and household survey, there's mention of specific types of pathologies that are problematic. It turns out that when you look at pneumonia, it's one of those common, apparently, pathologies that are normally handled by general practitioners. So if it's a suspected case of pneumonia, your typical general practitioner will come in and interpret the medical image rather than send it to the people in the Department of Radiology, because they would much rather they focus on the more important cases, if I can use that phrase. So thank you so much for that question. Wonderful stuff. I think there's a question from Henry. Please.
Okay, thanks so much. Are you able to get me from that end?
Loud and clear.
Thanks so very much. My network was bad. At first, I was raising a hand here. But this question is going direct to Mr. Andrew. One of the benefits of the system, it did indicate that there's accuracy and efficiency, and also better informed treatment. According to the evaluation made, is it safe to say that this system is maybe 100% safe working, or maybe there are some few hiccups that the system is still having? Thank you.
Right. Thank you for that question, Mr. Henry. So the system itself is not 100% yet. And I think that's one of the reasons why we made mention to the fact that there's still improvements being made. So on the part of the models themselves, even the accuracy for the models still have room for improvement. And there's a lot that can still be done to the tools themselves to improve them and give them maybe features that would be better than the ones that they have now. So it's still work in progress with a lot of room for improvement, really. But as a functional prototype kind of tool, yes, it is working. It's able to actually confirm that this is workable, this is doable, and it can be implemented on a large scale. So proof of concept is there, but the system itself is not 100% working yet. There's still enough room for improvement, and it'll be getting better just like any other system, you would say, with time. More training, improvement of certain features, because the more the practitioners interact with tools like this, the more even you as a developer would learn about the ways in which you would further improve such a tool to suit the needs of the people that use it. So yes, there's still enough room for improvement. Thank you.
And if I can chime in, maybe you can also navigate to the PAX platform and right the interface itself. It turns out that when you speak to these experts, right? If you go to the homepage, the excitement out of the things that we've been doing the last 2 years, most of the excitement is this tool. Now, this was probably one of the easiest things we've had to do in the project, right? But it goes to tell you just how bad the situation is. So our colleagues are excited at the fact that they no longer, very, very soon, they will no longer have to wait for a doctor to send, they'll write a request. They have messengers apparently at UTH, right? You prepare a request, maybe you're in pediatrics or something. I don't know if you've been to UTH here. Hospitals are further apart, right? You write a request, that request is sent to the Department of Radiology by messenger. It's distributed to a person who is going to be examining the patient. Patient comes in, the examination is done, they'll generate an image which is burned on CD. So we're replacing that process with what you're seeing here together with the RIS. But in terms of what Andrew has done, it turns out we're going to deploy this, and we can actually deploy the plugin itself, right? But the thing is, the plugin he's developed is dependent on how good the models are. Now, it can be deployed and used really, but we haven't really gotten to a stage where we can comfortably say we can deploy these models and they can be used. But hopefully by the time Malaizyo is wrapping up his scope of work, hopefully towards the end of the year or early next year, then we may possibly get to that stage. So thank you so much for that question. If there are no further questions, this is
there's been a question from Mainza Chila for quite a while.
Oh, I thought he didn't put his hand down or something.
Oh, sorry, no. Let me.
Oh, okay. See, there's also a question in the chat.
Chela. Yeah, please, Chela, go ahead.
Okay, am I audible?
Very much so.
Hello? Oh, thank you. I just in case I missed out one or two points, maybe that is if it was what I'm about to ask was covered. I would like to find out something, but to that, I'd like to first commend the people behind the project. With what I've learned so far from class and from some other research I've done, surely our colleagues have done a good job, and I encourage them to continue. And I hope to see this project be perfect in the future and be used surely to change the way things are done and to surely speed up the diagnosis process. Then my question is, with what we are building, in your research, when you did the research on existing systems, I'd like to find out what your findings were. Do we have such systems existing somewhere, or this is the first of its kind? Just that. Thank you.
All right, so maybe I can answer that one. All right, so thank you for the question. So when it comes to this particular system being the first of its kind, it's not really the first ever system to be implemented in this manner. So there has been implementations that work similar to the way this one is working, but you would find that most of those are actually commercial softwares. And so this was an innovation of trying to look at the commonly available or easily accessible tools, tools that are commonly used by radiologists, let's say in the Zambian context, or hospitals like here, UTH, tools that are easily accessible, in trying to implement a solution that would have solutions that are specific to our environment. For example, if you look at the training of the models, you'll find that there might be pathologies, for example, that are common in certain areas and not so common in other areas. So the idea was trying to find a solution that would best fit our environment or our location, for example. And that involves, in the future, that would also involve, let's say, training data sets based on cases from local databases, for example, cases that are common to the Zambian or this region of Africa type of context, as well as making sure that we have these tools that can be easily accessed by most people, as opposed to having limited options to only the tools that are working on a commercial basis. But yes, there are some tools out there that work in a similar way. They have a mixture of AI and enhancements that do something similar or even close to this, but most of them are commercial tools. Thank you.
Well, thank you. Thank you so much. I appreciate that answer. And please continue with the good works. I love it. Thank you.
Thank you very much.
Colleagues, there's a question from Harris. Please, Harris. Maybe we'll take one last question from Harris and then we can close this. Yes, please.
Yes, my question is around the radiologist residents involved in the study. What was the sample size? Like, how are they selected?
Okay, there were two studies here, and it depends on the part you're describing, but if it's the part I presented, where we went through the NASA-TLX questionnaire as well as the term 2 form, so there were 13. So graded in different gradations. We actually managed to interview all but one of the training radiology residents, forgive me, here at UTH, all but one, and we managed to do some radiologists as well as certain practitioners who were referred by the radiologist, who it's part of their flow to interpret chest X-rays and who it would be expected for. So yeah, the number might seem small, but there are very few of them here. Radiology residents. Though at the time we were doing the study, that was all, but now there's, I think, one or two new people. But yes, we managed to get almost everyone here, a number of qualified radiologists, as well as some practitioners from other departments. Yeah, but we continue to increase the number as well. It's just that times have been a bit hard. But yeah, they're very few. As was stated there, at last check, there were 11 catering for in public service in the entire country. So yeah, thank you very much.
All right. In closing, just to let you know here that if you go to a place like UTH, in any given year, you'd have, I think, an average of about, the cohorts vary, right? But last time we checked, I think we had a total of about, the highest we've had, also interacting with people from UTH, first year through to fifth year, is I think about 15, maybe 16 or 17 or something. So there's a limitation in terms of which entities we can actually use for evaluation, which is why in some instances we actually evaluate what we're doing with general practitioners. But on that note, again, want to sincerely thank you for being a part of this. We shall send out, we still have, I think, about 2 more talks. They may not necessarily be in line with radiology, but to do with data mining nonetheless, machine learning and AI stuff. So would be really, really be grateful if you could join us. Is it next week or after next week? Thank you so much, everybody, and good night. Bye for now. Some space, but